Hello students, this video is over lesson 57, negative exponents, scientific notation for small numbers, and this is for my 7th grade math class, Saxon Course 2. So scientific notation, remember, is a form of writing numbers as the product of a coefficient and a power of 10. It is often used for very large and very small numbers. So just real quick to step aside here, we've already learned this. So if we take a look here at these two numbers, they're kind of large, so we're going to write them in scientific notation. So the first thing that we're going to have is this thing called the coefficient. Okay, so it's going to be of this form right here. So this first guy here is the coefficient, and it's the number being multiplied in front of the power of 10. So to make it, we're just going to move the decimal so that there's only one non-zero whole number digit. So really just one whole number digit. So if I'm only going to have one whole number digit here, it's going to be the 6. So we're going to have 6, but it's not just a 6. This number also has a 2 after that 6. So, but if this is the only whole number, it'll have to be 6.2. So that's my coefficient. Looking at this problem down here, my one whole number digit must be 7. But after this, I see a 0, 4. So this would be 7.04. But then we take this coefficient, we multiply it by a power of 10. Okay, so we got to figure out what this exponent here is on this power of 10. So n is the exponent of the power of 10. It tells us the number of times the decimal and the coefficient would need to move in order to become the original number again. So if we come back over here, so if this is a 6.2, if I put the decimal right here, then how many times would I need to move it in order to turn it back into this? Well, it would have to move once, twice, 3 times, 4 times, 5 times, 6 times, 7 times. So this will be times 10 to the 7th power. For our other number here, this is where we put our decimal in the coefficient. So it would need to move once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, 10 times. So this will actually be times 10 to the 10th power. So that's how scientific notation works for very large numbers. So now let's take a look at the notes here. To find the count, how many spaces would be needed to move the decimal to the end of the coefficient. Then count the number of zeros needed. Add these two amounts together. So the exponent is positive for very large numbers. So when we've got a very small number, all we're going to do is use a negative exponent. So if a positive means move that decimal to make it bigger, a negative will move that decimal to make it smaller. So if we take a look at our first example here, so we got a bunch of zeros, ignore the zeros, so my first whole number digit will have to be 6, followed by a 2, 5 in the decimals. Now, if I've got my decimal right here, how many times would I have to move it to go back to the original? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times. So this is times 10 to the 15th, but because we want it to get small, it'll be the negative 15th power. The negative 15th power. Down here. Down here. All right, here we go. So, by the way, if you're getting the hang of these, I would recommend that you challenge yourselves. And before I really get going, pause the video, see if you can do it on your own, and then play again to see how you did. So here we go with this guy. Ignore all the zeros. So the first whole number digit will have to be the 2. But that 2 is followed by a 079. So 0.079. Now we put the decimal after the 2. So how many times would we have to move it to get it back to where it's supposed to be? Well, once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, 11 times, 12 times, 13 times, 14 times. And since it gets smaller, it'll be a negative 14th power. Third example, our coefficient here, one whole number digit will have to be a 6, and it's followed by a 3, so 6.3. And now we're going to move it. So this time I'm going to just go once there and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So it'll need to move 21 times but get smaller. Here, my coefficient, my one whole number digit will have to be the 3, followed by a 0.12. That means the decimal's right here. I need to move it back to its original spot. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 3.12 times 10 to the negative 17th power. And my last example, the only whole number digit that I have here that's not 0, or excuse me, the only digit I have here that's not 0 is 1. So that has to be my coefficient. Well, a 1 naturally has a decimal after itself. The decimal will be right here, so we're looking right here. So how many times we got to move that to get it back to its original spot? Once, twice, 3 times, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Ladies and gentlemen, I would recommend that you sometimes actually go back and double count one more time. So once, twice, 3 times, 4 times, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Just because with all those zeros, it's easy to kind of get your eyes a little crossed and miss one there. So a double check there really is a good idea. All right, we're going to move on to the next side of our paper here. And we're going to look at some rules. So here we see our math pyramid. So remember, the first thing you learned in school in math class was you learned how to add. Then you learned its inverse, how to undo addition, and you learned subtraction. After a while, we built off of that skill, and we learned that if we repeatedly add, we can express that as multiplication. And then a little while later, we learned that that has an inverse, something that undoes it, and that's division. And then after a while, we learned that if we repeatedly multiply, we can express that as an exponent. And then exponents also have inverses called roots. So it turns out, if we think about this pyramid, that when we're doing things with powers, so a number that has an exponent, that this will help us to find the rules for our powers. So the way this works is, whatever you do with powers, you can do one step below it with the exponents. So if I'm multiplying the powers, so there's my first power, there's my second power, and we're multiplying them. If we're multiplying the powers, we can instead add the exponents. So this power times this power, notice they have the same base, they're both x for the base, will equal same base x, but we just add the exponents. So we can combine these two if they're being multiplied by adding the exponents. Over here, if we divide powers, we can instead subtract the exponents. Remember, fractions mean division. So x over a divided by x over b, again, notice that they have the same base. They got to have a matching base. So we can combine these, but since it's division, division leads to subtracting exponents. So it'll be the top exponent minus the bottom exponent. Over here, we have power. So if you do a power to a power, we can instead multiply the exponents. So x to the power of a, then raised to the power of b, actually becomes just x to the power of a times b. So a power of a power of a power, ends up multiplying the exponents. And then the last property, while true, we're not going to do too much with that just yet. So, but just for the sake of going over it very quickly, if you do a root of a power, it ends up leading towards division. So down here, if we apply those properties, here I've got a power, I've got another power, and we are multiplying. So think about your pyramid. If we multiply the powers, we can instead add the exponents. So this would be x to the power of 8 plus 5, which is 13. Next problem. If I have x to the 19th power times x to the 7th power, again, we're power times power. So if we multiply powers, we can instead add the exponents. So this would be x to the power of 19 plus 7. Well, 19 plus 7 is 26. And then our last one here in this row, x to the power of 6 times x. Now this doesn't look like a power. However, if we imagine an invisible 1 there, then we can see what power this really is. So x to the power of 6 times x will become x to the power of 6 plus that invisible 1. So this actually would become x to the power of 7. Dividing powers results in subtracting the exponents. So x to the 8th power over x to the 5th power will be x to the power of 8 minus 5. Well, 8 minus 5 is 3. Over here, x to the 19th power divided by x to the 7th power will become x to the 19 minus 7 power. Well, 19 minus 7 is 12. And then last one in this row, remember we're going to imagine that this is an invisible 1 here. So x to the power of 6 divided by x will be x to the power of 6 minus 1, or 5. So here we go. We're going to explore a couple other things now using these properties. So we know using the division, oh, sorry, I totally missed that line. Let's finish this line first. So when we do a power to a power, so x to the 8th power, then raised to the 5th power. So a power to a power means we're going to multiply them. So 8 times 5 is 40. X to the 19th power, then raised to the 7th power will be x to the power of 19 times 7, which is 133. And then finally, x to the 6th power, then raised to the 2nd power, will become x to the power of 6 times 2, which is 12. And now we're going to move on to this next section. So again, we're going to do some more division. So division means we're going to subtract our exponents. So if we take a look at this here, I have x to the power of 10 minus 7. So 10 minus 7 is 3. Now here though, I have x to the power of 7 over x to the power of 10. So again, this is going to lead to subtraction, but the order matters in subtraction. So this time, this is not going to be 10 minus 7, it's going to be 7 minus 10. Well, if you have $7 and I take away 10 of them, well, you don't really actually have enough to give me. You're going to have a little bit that you're going to have to owe me. So owing somebody is a negative. So this is a negative 3. So, and as just a reminder for the future, the reason we got this here was because this was 10 minus 7. We got a negative because this was 7 minus 10. Moving over here. So x to the 17th over x to the 4th will be x to the 17 minus 4. I'll go ahead and write that in red. 17 minus 4. Well, 17 minus 4 is 13. This guy here will be x to the power of to the 4th over x to the power of the 17th. So we're going to subtract. This time, though, will be 4 minus 17. So if you have $4 and I try to take away 17 of them, I'm going to take all 4 of your dollars, but you're going to owe me $13. So ladies and gentlemen, here's what I need you to see. Positive 3, negative 3. Positive 13, negative 13. So what is the relationship between these two problems? And what is the relationship between these two problems? Well, the exponents become negatives. But if you look at the fractions, what's going on with the fractions? Well, x to the 10th over x to the 7th, and down here it seems to flip. So what's that called when we take a fraction and we flip it over? Hopefully you just said reciprocal. So what we've discovered here is that negative exponents make reciprocals. Negative exponents make reciprocals. So down here, we're actually going to do these problems twice. So first of all, x to the 9th power of x to the 9th power. So remember, when we have a power divided by power, we subtract. So, well, 9 minus 9 is 0. Here, 32 minus 32 is 0. 2 minus 2 is 0. 11 minus 11 is 0. But what else do these equal? Well, x to the 9th over x to the 9th, this is something over itself. Something over itself is always 1. Something over itself is always 1. Something over itself is always 1. And something over itself is, well, still always 1. So ladies and gentlemen, what we've discovered here is another rule of exponents. A moment ago, we discovered that negative exponents make reciprocals. Now we've discovered that something to the power of 0 will equal 1. Now, ladies and gentlemen, you don't need to understand right this moment why this is true, but you do need to accept and memorize that it is true. And we're going to move on to the next page here. So on the next page, we're going to take a look at negative exponents a little bit more in detail, and we're going to do some practice problems together. So first of all, these rules only apply when the thing I've got my negative exponent on is not 0. So when we have a negative first power, it creates a simple reciprocal. So instead of having x, we get x over 1. And so to help you kind of understand what's going on here, if I look at my dry erase board again, if you think of x, if you think of a variable, variables are almost like whole numbers. So just like if I had 5, I could turn that into a fraction and make it 5 over 1. You can take x and make it x over 1. So just like the reciprocal then of 5 is 1/5, the reciprocal of x is 1 over x. Which is why our negative first power gets us 1 over x. But what happens when this isn't a 1? It's still negative, but it's not a 1. Well, that's what we're going to see here. So this time what's going to happen is I'm still going to have that 1 on top, but the exponent will stay with the x. It's still an exponent. It's not going to become a numerator. It's still the exponent of x. But the way you can think about this is this x is traveling from the numerator, right? Whoops, knocked my camera there. So this is traveling from the numerator to the denominator when we take a reciprocal. Well, just like when you get in your car and you travel someplace, it takes fuel, it takes gas to get someplace. But if you go, you burn up that fuel. So when I take this reciprocal, then this negative gets burned up. So when you take the reciprocal, no more negative in the exponent. But if the exponent is on x, it'll still be on x over here. Now, two more things, and this will help you, maybe not so much on the homework, but it'll help you more in the future. So I want to prepare you for that. When you have a fraction, and the exponent is only on one part of that fraction, then only that part of the fraction is going to move. So typically in most reciprocals, well, in a full reciprocal, your numerator becomes your denominator and your denominator becomes your numerator. They just switch places. But here, the negative exponent is providing the fuel to move the y. But there is no negative exponent on x, so there's no fuel to make it move. So that means x is going to stay right where it is. However, the y, being a denominator, will flip up and become a numerator. And so really we should have one more spot here. The empty denominator then just becomes a 1, which we're just going to add that in there. And then anything over 1 really is just itself. Now over here, this time, the x has the negative exponent. This is what has the fuel to move. So this x is going to move from the numerator to the denominator. However, y doesn't have a negative exponent. Y does not have the fuel to move, which means y will remain where it is. The empty numerator becomes a 1. Empty denominators and empty numerators always become 1s. So now let's take a look at our last property, and then we'll do some practice problems. So this one's real simple. We said it on the other page, but we're going to get it on here just a little bit more formally. So the law of exponents for the power of 0 says that for x not equal to 0, so x can't be 0. But if it's anything other than 0 and you raise it to the power of 0, the answer is 1. So we have two properties there. I'd like you to please grab your highlighters and let's just put a yellow box around there. That's a rule that's kind of new to us. And then we'll put an orange box around that. That's our other kind of new rule here. So remember, negative exponents make reciprocals. So what I'd like you to do right now is I'd like you to give this a shot. Just these first 4 examples right there. I'm blocking them right there with my fingers, blocking them off. Put my hand over there. Just those first 4 examples. I want you to give those a shot. Go ahead and pause the video and see what you can come up with. And we'll talk about them when you hit play. All right, now if you followed my directions, you've given those a shot. Let's take a look at them together. So 3 to the negative first power. Remember, if it's the negative first power, it's just going to make a reciprocal. So 3 would normally be 3 over 1. So if we flip that over, 1/3. That is just 1/3. This next one, remember that if this is something other than 1, that this exponent sticks with the x, but when it moves, it burns up that negative. That's the fuel that allows it to move. So this would actually turn into 1 over 3 to the 4th power. Now, hopefully you got that, and you realize that that could be simplified further. So 3 to the 4th power means 3 times 3 times 3 times 3. Well, if I take 3 times 3 times 3 times 3, well, you might go 3 times 3 is 9, and 3 times 3 is 9, and then put your two 9s together. 9 times 9 is 81. So this is 1/81st. Likewise, down here, a negative first power would just make this 1/2. But a negative third power, the negative would make a reciprocal, but the 3 would still be the exponent of 2. Now, 2 to the third power means 2 times 2 times 2. 2 times 2 is 4, times 2 again is 8. So 1/8. All right, now give these next 4 a shot. Give these next 4 a shot. Pause the video. All right, hopefully you're back now. So remember that a negative first power just makes a reciprocal. So if this is 1/4, its reciprocal would be, well, flip these around, 4/1, or just 4. The reciprocal then of 1/4 to the negative second power, well, the negative would flip this to make it a 4, but the second power is still on it. Well, 4 to the second power is 4 times 4, or 16. Here, the negative exponent will just make a reciprocal, so 5/2, which can then be simplified. So 5/2 is, well, 2 goes into 5 2 times with 1 left over. The denominator was a 2, so it still is a 2. So that's actually 2.5. And finally, my last one. My last one here, this is 2/5 to the negative third power. So I'm going to flip it, but then my exponent 3 will still be on this. Now, since this is a fraction, I need to put this in parentheses, so it tells me this 3 is happening to both of those. This exponent 3 is happening to both of those. So, for the numerator, 5 halves times 5 halves times 5 halves is going to mean 5 times 5 times 5. 5 times 5 is 25. Think about quarters now. How much is 5 quarters? $1.25. Down here, this will be 2 times 2 times 2, which we just said a moment ago was 8. Now this needs to be simplified, so we need to do some division. You can actually do a little bit of short division here, if you feel comfortable with it. So 8 does not go into 1, but 8 does go into 12 once. Now, that's going to be 1 times 8 would be 8, so 12 minus 8 would leave me with 4 left over. So I'm going to treat that now like a 45. 8 goes into 45 5 times, because 5 times 8 is 40, which means we have 5 left over. And what was the denominator? 8. Now, if you didn't follow the short division there, that's okay. Just do the long division. All right, next column here. This time, we're going to do just these 3 problems right there. However, we're going to do them like we did these 2 examples here. So make sure you follow these 2 examples here to see how to do those. So again, give those a shot, give a pause. And we're back. So here we go. The negative exponent is only on the 2, so the 2 is going to be the only thing that moves. So the 2 will move to the bottom, where the 3 will stay. Empty spaces get filled with 1s. And so this becomes, well, 2 times 3 is 6. So this is 1/6. Over here, the negative exponent is on the 3, so it's only the 3 that will move. The 2 will stay on top, the 3 will move up to join it, and empty spaces get filled with 1s. Well, 2 times 3 is 6. 6/1 is just 6. And last of all here, since these both have a negative exponent, they are both going to move. The 2 will move to the bottom, the 3 will move to the top, and then we got to simplify. So 2 goes into 3 one time with 1 left over, and the denominator is a 2. All right, next example. Next example, I want you to do just those two, and you're going to use our power of 0 law. So 5 to the power of 0 is 1. 9 to the power of 0 is 1. Hopefully you got that. Those should be nice and easy. As long as it's not 0 that we are have as a base. Anything else to the power of 0 is 1. And last of all, down here, there's a couple different ways that we could do this one. So one, we could use the property that we learned earlier. And we could say that 2 to the negative third power times 2 to the third power, this is a power times a power. So this would be 2 to the power of, well, negative 3 plus 3. Because when we multiply powers, we add the exponents. Well, a negative 3 is like owing me $3. And a positive 3 would be like getting paid $3. So if you get paid $3 and you owe $3, you can cancel out your debt but have nothing left over. So this will be 2 to the power of 0. So we already know from our property up there that this would just be 1. The other way that we can do this problem is we can go ahead and deal with this negative exponent. So a negative 3 will make this 1 over 2 to the third power times 2 to the third power. 2 to the third power we know is 8. So this is really 1 over 8 times 8. Well, guys, these are reciprocals. Anytime you multiply reciprocals together, the answer is 1. So either way we look at it, the answer is 1. And that, ladies and gentlemen, is the end of our lesson.